Hi, and welcome to our second lesson in Chapter 2. The title of today's lesson is Conditional Statements, and I have three groups of people who are making statements. I will tell you that two of them are conditionals. A conditional is a statement that has an if and a then in it. This group of people, there is no ifs, ands, or buts about it. They are just stating, we are cool. And that, folks, is called a proposition or just a statement. It's a statement of, well, maybe a fact. Statements don't always have to be true. These two groups are issuing conditionals. A conditional or an implication is an if-then statement, and this group says if you skate, then you're cool. In other words, in order to be cool, you got to be skating, right? This group, well, you can see what they're saying. It's still a conditional, has an if and a then, but it's all termed in the negative. If you don't have an iPhone, then you're not cool. Well, I'm not sure about the truth of that either. However, I do know that in a conditional, an if-then statement, if-then, the if part is called the hypothesis. The if part. The then part is the conclusion, and on we go. All right, today's lesson is going to include a lot of language, and we're going to learn some new words, so I'm going to ask you to pay a special attention to this page. A statement or proposition may be either true or false, as we said on the previous screen. Just because somebody said something doesn't mean it has to be true. Its truth or falsity is called the statement's truth value. Again, all that truth value just means, is the statement true or false? And in math, as you recall, if a statement is going to be called true, it has to be true every single time. It not just hit or miss, but every single time. In fact, you can show a math statement to be false if you can think of an example where what should have happened didn't happen. That's called a counterexample. Counterexample. In my words, I define that by saying one time where what should happen doesn't. One time where what should happen doesn't happen. And I'd like to illustrate that with this little example here. Consider this statement. A number divisible by 5 is odd. Okay, that is a statement. To decide whether it's true or false, we have to decide if it's true every time. Any number divisible by 5 is odd. And I'll betcha that you're already thinking of some counterexamples. This is a false statement because numbers like 20 that end in 0 are divisible by 5, but they're not odd. That's a counterexample, and all it takes is one case where what's supposed to happen if you're divisible by 5 according to this is that you're odd. You have one case where it doesn't work. That's all it takes. The next word that I'd like to introduce you to is negation. The negation of a statement is another statement with exactly the opposite meaning. As in, one way, the easiest way to negate a statement is to insert the word not in it. And I'd like to illustrate that with this one. Suppose somebody says, I believe in Santa Claus. To negate that, exactly the opposite meaning, I do not believe in Santa Claus. Right? Or I don't believe in Santa Claus. Negation is a statement with exactly the opposite meaning. I'd like you to think next about this statement. A polygon with exactly 4 sides is a quadrilateral. The question is, what is its truth value? That is it true every time, or are there polygons with exactly 4 sides that are not quadrilaterals? I would say that most of you are probably thinking this is true because it's true every time. dot, 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 every time, right? Because if a polygon has exactly 4 sides, by definition, that makes it a quadrilateral. I'd like us to take this statement and let's move into the next part of our lesson by writing this in conditional form. That is an if-then statement. We want to keep the one thing that we have to worry about is keeping the order correct. This talks about a polygon with 4 sides being something. So our if statement, the hypothesis of our statement, if a polygon has exactly 4 sides, according to this definition, then it is a quadrilateral. So we took the statement, we inserted if and then in the proper places. The start of this, the hypothesis, has to be the starting object of the sentence. The conclusion has to be the ending. And now we want to talk just briefly about logic. We've already defined and looked at conditionals. A conditional in words is something like this: if hypothesis, then conclusion. So we're letting P equal hypothesis here and Q equal conclusion. If you were going to write that in symbols, the arrow means implies or leads to is a good way to think about this, leads to. In symbols, we'd say that hypothesis leads to conclusion, or P arrow Q. I've got an example here, and I'd like us to think about truth value as we go through this. If a number is divisible by 6, then it is divisible by 3. Hypothesis, divisible by 6. Conclusion, divisible by 3. Is that true? It has to be, folks. If a number divides by 6, since 3 goes into 6, it will also be divisible by 3. Now, we are going to talk about 3 statements closely related to the conditional, but they switch the order of things or sometimes negate. The first of those statements is the converse, and the converse does switch the order. Switch, or sometimes I say switches the order. So in words, you'd say switching P and Q, hypothesis and conclusion, if Q, then P. In symbols, Q leads to P. We switch things right around, right? My example says if a number is divisible by 3, then it's divisible by 6. And you know what? I'm pretty sure that's not true, because 3 is a number that's divisible by 3. It's not divisible by 6. This one is false, folks. You can't say that. This way it was true, but when you turned it around, it wasn't. Now, the next statement that we're going to talk about, the next logical relative of a conditional, is the inverse. And this inverse goes back to the original ordering, but it knots both of the parts. Okay? It negates both parts. In words, if not P, then not Q. In symbols, the symbol for not is a tilde, so it would look like this. Not P leads to not Q. Okay? And in my example, if a number is not divisible by 6, then it isn't divisible by 3. Again, I think you can prove that to be incorrect by looking at a number like 9. 9 is not divisible by 6, but it is divisible by 3. That also is false. The last of the related statements is the contrapositive. And folks, it does it all. This one both switches and knots. And if you think about it in words, if we got a switch and not. If not Q, then not P. In symbols, not Q leads to not P. And folks, you've maybe heard the expression, mind your P's and Q's. They may have been talking about logic, because this is the introduction to a course on logic, which many of you will take in college, by the way. All right, here's my example. I'm going back to where I started. I have to switch and not. if a number isn't divisible by 3, then it isn't divisible by 6. Now that, I believe, is true. If 3 doesn't go into it, then 6 cannot go into it. I'd like you to take a look at this, folks. We're going to make a deal about this in a second, but if that conditional is true, then the contrapositive must also be true. Okay? They are a matched pair. If the conditional, the if-then, is right, then the contrapositive is also right. Let's go on, and we're going to take just a little example from what's in the book. I'm going to ask you to pause the video here. This is the statement we are working with. Angle A that measures 120 degrees is obtuse. We want you to begin by writing that as a conditional. Please do so. The truth value on that statement, 120 degree angle is obtuse. That is true. Now I'm going to ask you to pause again, and I want to just remind you the converse switches, the inverse nots, and the contrapositive does both, switch and not. And I would like you to do that with our statement. Okay, let's pause that video. All right, we're back. My converse, inverse, and contrapositive are here. I hope that your statements look very similar. The language doesn't have to be exactly the same. However, the meaning has to be. Okay, if angle A is obtuse, then it measures 120. Hey folks, are there angles that are obtuse who don't measure 120? Even 121, right? This is false. And the inverse, we knot both parts. Original order, but we knot. If angle A doesn't measure 120, then it's not obtuse. Well, that also is hooey. It could be 130, which is not 120, but that's not obtuse. Well, yes, it is. This is false. Okay. And finally, the contrapositive, both switches and knots. If the angle A is an obtuse, then it doesn't measure 120, and that is true. If it's not an obtuse angle, it cannot measure 120. Once again, I think that you will notice the truth value of the conditional and the contrapositive are true. Okay, that is, a conditional and its contrapositive are equivalent statements. That is, they both have the same contrapositive. They both have the same truth value. Okay? They're either both true or both false. The converse and inverse are also equivalent statements. They both have the same truth value, either both true or both false. This is the last little tidbit we want to give you today. When a statement and its converse are both true, that is, if it's true this way and the opposite way, original order and opposite order, that's called a biconditional. You can write a statement called a biconditional by joining hypothesis and conclusion with the phrase if and only if. It is true that any mathematical definition can be written as a biconditional. And that's the end of our lesson for today. We need you to get out there and look at that. You try, and I'll see you in school.